So far when we use the divergence theorem, we've always started with a closed surface because to use the divergence theorem, the surface needs to be the boundary of a volume, and so the surface will always be closed. But you can still use the divergence theorem even if your surface isn't closed. You just have to add some surfaces so that it is closed. And the trick in that situation is to choose surfaces that are easier to integrate over. So here's one example of this. This particular integral actually would be doable on its own, but I don't want to use an example that's too complicated just because the point of this example is not necessarily the particular integral that we end up writing down. It's sort of the trick of adding surfaces to use the divergence so that you are able to use the divergence theorem. Okay, so let's find the integral, the surface integral of this vector field over this vector field f over a surface that is the part of the plane 6x plus 3y plus 2z equals 6 that's in the first octant oriented upwards. So even without knowing exactly what this plane looks like in this octant, since these coordinates, or since these coefficients on x, y, and z are all positive, and this 6 is positive, it's going to look something like this. Okay, this plane is going to cut out something like this in the first octant. But it's not a closed surface, of course, right? You might hope, well, since it's not a closed surface, we might be able to rewrite this surface integral as a line integral around the boundary of the surface, but the divergence of this is not 0, so f is not the curl of some other vector field, right? If it were the curl of something, then its divergence would be 0, but that isn't the case. And so we can't use Stokes' theorem because the surface integral in Stokes' theorem is the surface integral of a curl. Okay. On the other hand, this isn't a closed surface, so we can't immediately use the divergence theorem. But there's kind of a nice way to close this surface up so that it does enclose a volume, right? Although this surface on its own isn't closed, if we add these triangles coming from the coordinate plane, we do get a closed surface. So let's name those. Let's call them S1, S2, and S3. Okay. And then S together with all of these other surfaces is the boundary of a volume, and the volume is this tetrahedron in the first octant. Okay, so now the divergence theorem tells us that the integral over s plus s1 plus s2 plus s3 of our vector field dot n d sigma is equal to the triple integral over v itself of the divergence of f dv. Okay. All right, so this integral on the left, right, this is the integral over s of f dot n d sigma plus the integral over s of s1 of f dot n d sigma plus the integral over s2 of f dot n d sigma plus the integral over s3 of f dot n d sigma, and that's all equal to the triple integral over the volume of the divergence. The divergence of this vector field, it looks like it's going to be, let's see, 2x plus x plus 1, so 3x plus 1 dv. Okay, so when it comes to doing this volume integral, this is a pretty straightforward volume integral, but let's think about all of these surface integrals. So this first surface integral, this is the one we want. So it's okay that we don't know this yet. So this is the one we want to find. So we know we can do the volume integral. Let's think about these three other surface integrals. So for this surface integral, S1 was, this is a region in the plane in the xz plane, right? So we have x, y, and z. So this is in the xz plane. And a normal vector for that plane, well, we have to choose an outward pointing normal vector. So that's going to be 0, comma, minus 1, comma, 0, right? For S1, our normal vector has to be pointing to in the negative y direction. Okay. So if we take our vector field, x, let me copy it down here because I'm going to be needing to refer to it. X squared, xy, and z. Okay, so if we take our vector field in the xz plane, well, the xz plane, remember, that's where y is equal to 0. So this is going to be the integral of, our vector field is going to be, well, x is 0, so 0, comma, x times y, but x is, I'm sorry, this is not right. My eye keeps going to n, and I am plugging 0 in where I shouldn't. Okay, so in the xz plane, x squared is, well, it's x squared. In the xz plane, y is 0, and when we plug that into our vector field here, we get 0 for this coordinate. And then z, well, z is z in the xz plane, but we're dotting this with 0, minus 1, 0, right? D whatever. What would go here? I guess dx dz. But the integrand here is 0, right? This dot product is 0, and so this surface integral is a surface integral of 0, so it's 0. Okay, what about this surface integral? This is S2 is in the x equals 0 plane, so this is where x equals 0. And while we're at it, let's do S3. S3 is where z is equal to 0. Okay, so for S2, this is the yz plane, and for z equals 0, that's the xy plane. So the normal vector for the yz plane is in the x direction, right, in the x direction, but right, S2, that's this back surface, and so we need the negative x direction. So for our normal vector for this integral, we get minus 1, 0, 0, and then the vector field is in this x equals 0 plane is going to be, well, x, we're plugging in 0 here, so 0, comma, 0, comma, z. But then again, the dot product of these two is 0, so this is going to come out to be 0 because the integrand is 0. And then finally, in the S3 plane, S3 is the bottom surface, so we need to orient it downwards. And so the normal vector in this case is going to be 0, 0, minus 1. And the vector field itself in this plane is, well, x is a variable in the xy plane, so x squared. And then x times y, x and y are both variables in the xy plane. And then z is 0 in the z equals 0 plane. And again, this dot product is 0, so this one is 0. So since each of these surface integrals is 0, the one surface integral we didn't know, which was the surface integral of S, f dot n d sigma, is equal to the integral over the volume of the divergence, which was 3x plus 1, I think. Okay, so now we can evaluate this triple integral, and right, often evaluating triple integrals is easier than evaluating surface integrals. So this integral should be relatively straightforward. Now, for this particular example, this integral, or this volume, let's see, this bottom line here, we can put the variables in any order. This line in the xy plane, that's this plane, but where z is 0, and so this is 6x plus 3y equals 6. So this is going to be y equals let's see, move the x's over and then divide both sides by 3. 2 minus 2x. Okay, whoops. X itself is going to go out. Let's see, in the x direction, looks like we're going to go from 0 out to 1, right? Because when x is 1, then 6 is equal to 6. So x is 1 and y is 0 and z is 0. So this intercept is at 1. So x is going to go from 0 to 1. dv, or dx on the outside. So now we're along a slice like this. The y-coordinate is going to go from 0 out to this line, which remember is this line. So y is going to go from 0 to that line. So from 0 to 2 minus 2x, and that's dy. And then z is going to go from 0 up to the plane, right? And the plane, let's see if we solve this plane. For z, we get z equals 3 minus, let's see, move the 6x over and divide by 2, 3x minus, move the y's over and divide by 2, 3 over 2y. So 3 minus 3x minus 3 over 2y. So 3 minus 3x minus 3 over 2y, and the smallest z value was 0, dz, and our integrand is 3x plus 1. Okay, so again, this is a routine triple integral, so I'll leave this as an exercise. So you can see that the reason that this worked is because these extra surfaces that we used to close up our non-closed surface into a closed surface, right? The surface integral over these is somehow nice, and nice means the integral of the vector field over these surfaces is 0, right? So if you have a non-closed surface and you can close it with a surface over which the vector field has a nice integral, especially if it's 0, usually 0 is the goal, then closing the surface and using the divergence theorem can make your integral easier to evaluate than working through the original surface integral. So again, caveat, this particular surface integral actually is not undoable, it's pretty doable, but you can imagine more complicated surfaces where, if you had some big complicated surface but sitting over a circle in the xy plane, it might be easier to cap off your surface with the disk and then use the divergence theorem to switch to an integral over the interior of the volume.